Hey guys, how you doing? It's Coach Scott, and this is our fourth video in this series about the periodic table. So this one, we're going to be talking about the basis of how these elements trend along the periodic table in the different periods, right? And as we go down the groups, why do they act like they do? So this is going to be on the effective nuclear charge and Coulomb's law, which is my favorite law in chemistry because everything is really pretty much based on it. So over the next couple of days, we're going to be talking about how the elements trend in the periodic table, both left to right and up to down, or up to down, right? We'll be talking about the radius of the atoms, how big they are, right? The electronegativity, which is a new term for most of you, but we'll introduce that. The ionization energy and the metallic character of the atom or of the element, right? So these four trends are shaped by the interactions between the positive charge of the nucleus and the negative charge of the electrons. So how do these charges interact with each other? That's the question we're going to be answering over the next couple of days. Now, remember this. Just about every science you've had in elementary school, middle school, high school, like charges repel and opposite charges attract. The positive end of the magnet is going to attract the negative end of the magnet. All right. So the positive protons are attracted to the negative electrons. Now, the negative electrons are repelled by the neighboring electrons. They don't like each other, right? So again, these are just the basic facts we know. So atoms of an element are often depicted showing the total number of electrons in each energy level. And this is probably something you saw in 8th grade. Let's look at this diagram. So neon has the following electron configuration. All right, there's 10 electrons. So it has a 1s2, 2 electrons there in the first energy level, then the 2s2 and the 2p6. So in that first energy level, there's 2 electrons. There's 8 electrons in the outer energy level. Now this is a term you probably recall from previous science classes. Those outer electrons are what we call the valence electrons. Now let's take a little test here real quick. How many valence electrons does magnesium have? And these are just the electrons on the outer surface, if you would. I'll give you a second to check it. All right, come back on. And of course, you selected 2. There's 2 electrons on the outer surface of the atom. Which of the following elements has the largest amount of inner shell of electrons? These are the electrons that aren't the valence electrons. Aluminum, silicon, or phosphorus. If you look at it, they all have the same number of inner shell electrons, so that would be D. So, when you're talking about these multiple electron atoms, the electrons are attracted to the positive nucleus and repelled by other electrons. So the nuclear charge that an electron experiences depends on both factors. Okay, so the valence electrons of sodium, element number 11, is attracted to the positive nucleus, but it's repelled by the negative inner electrons. Right, so if you look at the configuration for sodium, it has 1 valence electron. So there's 11 protons in the nucleus. All right, so those 11 protons are attracting the valence electron. Now, there's 10 inner shell electrons, the 1s2, 2s2, and the 2p6. These 10 inner shell electrons are repelling the valence electron with a charge of 10 minus. So the total charge on the valence electron, or what's attracting it, is plus 11, the number of protons in the nucleus, plus the number of the inner shell electrons, which is minus 10. So the charge on that would be plus 1. So those inner shell electrons keep the valence electron from feeling that full attractive force of the positive protons. So what's happening is the inner electrons are shielding the valence electrons, the electrons on the outer edge of the atom, from the nucleus. So those 10 inner electrons keep that one valence electron from feeling that full attractive force of the protons in the nucleus. Now this is something we call the effective nuclear charge, or Zeff, or ZF, or Z effective. I just call it Zeff, right? So the effective nuclear charge is the amount of charge that the outer electron actually feels. So we can do a formula for this. The formula for the effective nuclear charge is the Zeff equals Z, which is, if you recall from that first unit, is the atomic number, which means the number of protons, minus S. S is the shielding constant, or the number of inner electrons that shield the valence electrons for the protons. So for sodium, the Zeff is 11, which is the atomic number, minus 10, the number of inner shell electrons, or the S, are positive 1. So let's look at beryllium, boron, and carbon. They're in the same period of the periodic table. Let's look at their shielding constants, or the number of inner shell electrons. So beryllium is element number 4. It's got 2 inner electrons from the s orbital, the 1s energy level. So let's see how many. That's 2. Boron, element number 5. Again, there's only 2. There's only 2 electrons in that inner shell, right? In that first energy level. So its shielding constant is again going to be 2. Carbon, element number 6. Again, 2 electrons in that first energy level. So that again is 2. So they have the same shielding constant, or that same number of inner shell electrons. So the elements in the same period are going to have the same shielding constant. We're still on the same row because the valence electrons are located in the same energy level. Now, each of these have a different atomic number, right? Because there's a different number of protons. So boron and carbon have this different subshells from beryllium, right? But they're in the same energy level. Beryllium's in the 2s. All right, boron is it's got 2s2 and the 2p1s. Carbon 2s2, 2p2. All right. They have the same. They're in the same energy level, that second energy level. So they have the same number of shielding electrons. They're on that same row. So let's calculate the Zeff of these, right? Now let's look at the effective nuclear charge. For beryllium, the Zeff is Z minus S. Well, we know that S is the same for all of them. So the Z for beryllium is 4. Well, that didn't work. Well, I'll just write on it and we'll do it. So the Zeff for this, a little pen thingy out. Okay, the Zeff for this will be 4 minus 2 for the shielding electrons equal 2. Boron has an atomic number, or a Z, of 5 minus 2 for the S, and that's going to be, of course, 3. And then carbon, 6 for the Z number, minus the S, or 2, equals 4. So what does that tell us? Well, what it tells us as we go to the right of the table, all right, there is the Zeff increases, the protons and the electrons, the valence electrons or the outer shell electrons, are attracted to each other with a greater force. Okay? So as you go left to right, there's more attraction for the electrons from the nucleus. There's less shielding effect. So what is the shielding constant for boron? We answered that earlier. Okay, it's on the second energy level. So just the s orbital, 1s, the first energy level is filled with 2 electrons. So that's going to be 2. What is the effective nuclear charge, or the Zeff, on electrons in the outermost shell for boron? Boron, the Z number is 5, right? So Z equals 5, okay? And the outer shell, S, the shielding electrons is 2. So again, the Zeff on this is going to be positive 3. C. What's the shielding constant for aluminum? Okay. Aluminum is in the third energy level. Okay. It's got a 3s2, 3p1. Okay. Valence electrons. So there's 10 inner shell electrons. So the Z number for aluminum is, well, we don't really need the Z number. There are 10 electrons, and let's just draw this really quick. All right, so that would be plus, plus 13 protons. It's got 2 electrons in the 1s orbital. It's got 8 electrons in the 2s2 or 2s orbital, and then 6 in the 2p orbitals. Those are what it's got there. So that's a total of what, 10. Then of course it's got 3 electrons rather, okay, in the third level. So these electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, they're what we call the inner shell. That's the S for that. So of course that's going to be C, 10. And we'll talk about this in class as we need to. So what's the Zeff, okay, on electrons in the outermost shell, the valence electrons for aluminum? Well, if you recall, the Z number is 13. The S we just calculated, well, maybe it'll write, maybe it won't, is 10. That's 13 minus 10. It's not writing for me, but that's okay. 13 minus 10 are a positive 3 charge on those valence electrons. Okay, so that of course is D. Which of the following would have the highest effective nuclear charge? Well, let's look at these on the periodic table. Aluminum, okay, aluminum 13. It's in the third energy level. Phosphorus 15 in the third energy level. Chlorine is in the third energy level, element number 17, and then argon is also in the third energy level. Well, the Z number for argon is 18. The Z number for aluminum is 13. They're going to have the same S number, which is going to be 10. All right, because those are the inner shell electrons. So the highest Z would be argon. Let's see if I can write on this. I can't, so we're not going to worry about it. Oh. And maybe I can get this thing turned on to where I can. Pen. Okay, so what we're talking about there, argon, the Z, this is argon, is 18. The S is going to be 10. 18 minus 10, that's going to be a positive, 18 minus 10, that's going to be a positive 8. Now, aluminum is the furthest to the left. Let's look at that. Aluminum, the Z number is 13. S is going to be 10. Those are the shielding electrons. So that's going to be a positive 3 for the Zeff, which tells me that there's more pull on the outer shell electrons for argon than it is for aluminum, and for all the other ones because they're between aluminum and argon. That would be D. In which subshell does an electron and an arsenic atoms experience the greatest shielding? The greatest shielding. Arsenic is in the 4th energy level, so those are going to be, well, either the 4s2 or the 4p level. All right, 4p, because those are the valence electrons. Okay. Oh, let's play with this one. 2 elements are studied, one with atomic number X and one with atomic number X plus 1. Assuming X is not a noble gas, okay, which element has a larger shielding constant? Well, they're on the same row. They're all on the same energy level. So C, they're both the same. They both have the same shielding electrons. C. 2 elements are studied, one with atomic number X and one with atomic number X plus 1. It is known that element X is a noble gas, so it's in group 18. Which element has a larger shielding constant? Well, it is a noble gas, so you're going to go down in energy level, so that would be the element X plus 1. X is a noble gas. The next electron, okay, or the next proton would put it in a different energy level, a higher energy level. That would be B. Okay, in which subshell does an electron in a calcium atom experience the greatest effective nuclear charge? Okay, calcium is number 20. All right, number 20, that's in the 4th energy level, the 4th period. So, the greatest effective nuclear charge. Well, we have to think about this, all right? The greatest nuclear charge is going to be the atoms, or the electrons closest to the nucleus. Okay, even though they're shielding electrons, that would have to be the 1s electrons, because there's nothing shielding it. So it's going to have more of a, it's going to feel more of that effect. So that's going to be A, 1s. Okay, compare the following elements: potassium, cobalt, and selenium. Which atoms feels the strongest attractive force between the nucleus and the valence electrons? Well, we got to find potassium. Potassium's in the 4th energy level, the 4th row, the 4th period. Cobalt, all right, that's in the 3D level. Selenium, oh, that's in the 4P, all right, that's in the 4th energy level. So the Zeff for 3D is going to be less, because this is going to be greater, right? Strongest attractive force between the nucleus and the valence electrons. All right, so cobalt doesn't have that many valence electrons. It's going to have 2 max. Okay, so potassium has 1 valence electron. It's got 18. It's got an 18s. So that's going to be 19 for the Z number minus the S of 18. That's going to be plus 1. Selenium 34 minus 18. You're going to have plus. You're going to have a stronger charge there, right? So the Zeff for that's going to be 34 minus 18. That's a lot. 34 minus 18. So it's going to be a plus 16. Plus 16. So selenium is going to have a greater attractive force between the nucleus and the valence electron. So all of this is related to what we call Coulomb's law. And when you get into class, you'll see 3 or 4 posters that I created that shows this law right here. And what Coulomb's law says is that the magnitude of the force between the protons in the nucleus and the electrons in the orbitals can be calculated, right? So Coulomb's law states this: the Coulombic force, that's what we call it, is equal to Coulomb's constant, a K, or a constant, it's always the same, Q1, the charge on the first object, times the charge on the second object. R squared is the distance between the two objects. So the distance is in the denominator and it's squared. All right, so does the distance between the nucleus and the outer electrons, that actually increases that force because it's in the denominator and it's squared. All right, so according to Coulomb's law, the stronger the charge of the objects, all right, the stronger the force is between the objects. The stronger the charge, the stronger the force. A. The greater the distance between the two objects, the weaker the force is between the objects. As that distance increases, okay, the force gets smaller. I might have misspoke on the previous slide. Because that distance is squared and it's in the denominator, it's going to make the force much smaller. So as the distance increases, the force gets weaker by a fair amount. Now let's play with this a little bit. So let's look at Coulomb's law and apply it to some of the atoms, and it's going to give us some good information that's going to come to play in the next couple of days. All right. So the Zeff for hydrogen is 1. There is no inner electron, so the S is 0. So the Zeff for hydrogen is +1. So the effective charge of the nucleus would be E. All right. And the charge of an electron is always going to be E. There's 1 proton, 1 electron. So I'll plug this into Coulomb's law, and I get K times E, or E squared. So the Coulombic force is going to be Ke squared over R squared. Now let's look at helium. Helium has a Zeff of 2. If you see how we calculate it, 2 protons, no inner electrons. So the effective charge on the nucleus is going to be 2e because there's 2 protons. And the charge of an electron is, we'll just call that E. So there is, put it into Coulomb's law, I've got K times 2e times E, right? Or I've got K over R squared. That comes up with the force is going to be 2 times K E squared over R squared. Now let's compare hydrogen and helium. All right, the force between the valence electron and the nucleus, that's 1 Ke squared over R squared. The force of the helium, the force between the valence electrons and the nucleus is 2 Ke squared. So the radius, okay, for both is the same since they both have the valence electrons in the same energy level. So the force between the nucleus and the electrons in helium is much larger than the force between the nucleus and the electrons in hydrogen. It's greater times 2. So how does that going to affect the radii of the atoms? Well, the greater the force of attraction causes the radius in helium to be smaller than hydrogen because that Coulombic force is pulling those electrons in closer to the nucleus. Let's look at lithium. Zeff, of course, is Z minus S. The Zeff for lithium would be 3, the Z number is 3, minus 2 inner electrons. So the Zeff would be 1. Well, do what we just did earlier, plug it into Coulomb's law. The force is going to be, if you look over here, all right, it's going to be Ke squared over R squared. Okay, now let's look at lithium. Okay, the Zeff is the same. Let's look at lithium versus hydrogen. The Zeff is the same, okay, E squared over R squared. However, lithium has the valence electrons in a higher energy level. So how does this affect the radii of the atoms? Well, as the distance increases, right, the higher energy level makes the distance between the nucleus and the valence electrons in lithium larger. So hydrogen will be a smaller atom than lithium, even though they're in the same group. Let's look at beryllium. The Zeff is going to be +2 because it has 2 shielding electrons. It has 2 valence electrons. Okay, so I'll plug this into Coulomb's law, and I come up with 2 Ke squared over R squared. If you need me to explain that again, I'll do it in class. So how does that make the radius of the beryllium and lithium compare? Well, we're on the same period. All right, but now I've got a greater attractive force between the nucleus of beryllium and the 2 valence electrons. So they're in the same energy level. Okay, just what you've got a greater attractive force, so that's going to pull the electrons closer to the nucleus. So beryllium, even though it's a larger atom in numbers, it's going to be smaller, in the radius is going to be smaller than lithium. Lithium will be a larger atom, if you would. Look at boron. Boron, element number 5. What's the Zeff? Well, there's 2 inner electrons, 2 shielding electrons. 5 minus 2 is going to be a +3. So that's going to be A. Now, let's do this. Compare the radius of boron to lithium and beryllium. They're right in line. They're on the second period. So lithium, think about the Zeff for that. The Zeff is going to be +1. All right, for beryllium, it's going to be +2. Okay. And for boron, it's going to be +3. So that means the radius of lithium is going to be larger than the radius of beryllium, because that nuclear force is pulling those valence electrons in, and beryllium is going to be larger than boron. It's got +3. It's pulling it. There's greater force pulling those outer shell electrons in. Okay. So that would be A. Let's look at carbon. Carbon, there's 4 valence electrons. All right, so pretty much that's going to tell me, okay, I got a +4 Zeff for that. All right, so that's going to be C. Now, let's compare carbon, boron, and nitrogen. Okay, boron is going to have a +3. I'll just do this real quick. Boron is going to have a Zeff of +3. Carbon is going to have +4. Nitrogen is going to have +5. So what does that mean? Boron is going to have less force pulling it, so it's going to, those electrons are going to spread out because they don't like each other, right? So there's going to be less positive force. So boron is going to have a larger radius than the next one, carbon. Carbon will have a larger radius than nitrogen. Nitrogen will have the smallest radius. So that's going to be C. Now these, we can play with them. Which of the following equations correctly calculates the Coulombic force between the valence electrons and the nucleus of an oxygen atom? All right, so how do we do that? Well, it's pretty much going to be C, because there's 6 valence electrons. E squared is going to be the charge of the electrons times the nuclear charge, so that's going to be C. That's probably not going to be asked on any type of test. given the atomic number of the smallest element of the second period. All right, pretty much, in case you haven't figured it out, on a same period or on the same row, it's going to be the noble gas, because it's going to have the largest Zeff. So that would be neon, which would be 10B. All right, guys, so that's Zeff. That's hard. 30-minute video. But now we'll talk more about that. We'll have some problems, and, well, we'll get through this. So now we should be able to compare the radial sizes as we go left to right across the table. The diameter or the radius of that electron gets bigger, or the electron of the atom gets bigger. As we go down a group, we start adding another energy level. The atomic radius gets larger as we go down a group. Almost makes sense. Okay, guys, this is Coach Scott. That's all. I know this was a long video, but guys, we learned a lot. So y'all have a wonderful day. Coach Scott saying toodles for now.